And it will allow us to do things that at the beginning sound a little bit strange. For example, it will allow us to prove that the code is good by showing that the code is very bad at certain positions. Okay, so it will allow us to kind of trade off what to show. So the topic is exit charts. And the area theorem. So let's start with something very simple. Let's assume I have n bits. And let's assume these bits, so these are all the xi, are all 0 and 1. Everything will be binary. And all my examples will be binary ratio channel. Everything I say you can do over channel on channels, and I'll remark a little bit about it, but things become just more complicated. And so I'll stick for mostly for the binary ratio channel. And so let's assume that we have 1 degree of freedom. So we have a single parity, we have a check. So it means that the xn so that you can think of the last bit or any bit being just the XOR of all the other ones. And then we're having the yi. And so the yi is simply the result of taking the xi. And in this case, I'll put it for the binary ratio channel. But again, this could be any channel. And I'll see out here my yi, right? And so now I have my vector y, okay, is the observation. And so what we're interested in, so what is now the best estimator for, so I'm interested in what is now the optimum, let me call it map. What is the optimum estimator for the bit I, right? So I'm interested in bit I. So these yi's, of course, can be now 0, 1, or question mark, right? And so what if I'm now interested in the estimate of bit I, right? Then what should be my estimate? And here I wrote something funny. I wrote tilde I, okay? And so tilde I means everything, all yj except yi. Okay, so this is what's called typically extrinsic. So I'm not allowed to look at the direct observation itself, right? I'm just allowed to look at the other observations of the bits, and via the code constraint, I want to compute bit I. That clear? So generically, think of this as a code. This is a very simple code, and I want to just via the code constraint to figure out what it is, but I don't want to look at the observation, right? The optimum estimate globally, of course, would be that I look at this, right? And then I can combine it still with the direct observation that I have, right? If the bit itself was received, right? Since it's in a ratio channel, I know it was either received or not, then I can, of course, do better. Okay, but it will be important that we look at the six. So, sorry, can you just? So can you just point where? Can you say stop? This, oh, because it's a binary ratio channel, so it's 0, 1, or question mark. If it's not erased, right? I know if it was erased. There are no errors, okay? If it's 0, 1, it's the correct bit. If it's question mark, right? So what would this be, right? So this is obviously, right? So this is just the sum of j of the yj, right? If all these yj received or not erased, right? If neither of them is erased, or it's either, otherwise it's just a question mark, right? Because, of course, every bit is just the XOR of all the other ones, right? So if I receive all the other ones, then I just take the sum of these other ones, right? And the bit xi must be the XOR of all the other ones. Is that clear? I'm just saying something trivial, okay? Sorry, no? Okay, if I'm saying this, then this is, of course, true for any bit, right? Any bit is the XOR of all the other bits, right? And it's the binary ratio channel. So if I receive the bit and it's not erased, then I know that that's the bit, right? So the optimum estimate for my bit I, if I can't look at anything, I can't look at the direct observation, is the only time I can tell something is if all these bits were actually non-erased, right? Right? If all these n-1 bits were not erased, then I know that the bit xi is the XOR of these bits. I take the XOR. But if any of them is erased, I can't see anything, right? Clear? I think I'm saying something too simple, so you think I'm saying something clever, but I'm not saying something clever. Okay? Make sense? Good. So now, what is the probability that this xi, now of course it doesn't matter, I could do this, I could have done this for any, right? It could have been xn, this is completely symmetric, so it doesn't matter which one. So what is this, right? So what's the chance that I cannot decode, that it's erased? Right, so that one of them is not erased is this, right? That n-1 are not erased is this, and only then I can decode, and I cannot decode like this, right? Okay, perfect. So, okay, so if we plot this, and here we're plotting this probability here, right? This looks whatever. You know, it's one here, and it's somehow, I don't know exactly, it's 1 here and it's 0 here. Okay? Something looks just, it's 1 there and it's 0 there. Okay, so now let's do the following. Let's compute this. Okay? So let's compute, so what is the integral from 0 to 1? Right, so that's of course 1 minus, and that's this, if I have 1 minus epsilon, epsilon doesn't matter. Okay, so I get, if you just do the computation, I get n-1 over n. Okay? So I just here, if it's 1 minus n, that since I integrate over everything, it doesn't matter if I integrate over epsilon, 1 minus epsilon, right? Okay, so is n-1 over n, does this have any significance for this case? Okay, so I get n-1, we don't know why we compute this thing, but does n-1 over n have any significance for this case, right? So we have this is a code, right? It's a very simple code, right? A single parity check code. Okay, it has length n. What are other important parameters in a code? Okay, so this is exactly, so here the rate. Okay, now, okay, fine, you know. I mean, we just picked one example to get the rate. Okay, but so this is exactly the equivalence that we'll talk about. So I'll just show you now how in general, so this would be the exit curve in general, and I'll show you in general how we define it. So this will be the exit curve here. And so it will turn out that in general, if you take any binary linear code, and so right now I show it for the binary ratio channel, but you can do these things for any other channel as well, that if you plot here, the entropy, so entropy here just means, you know, instead of the capacity of the channel, so this is a binary ratio channel, right, with erasure probability epsilon. The capacity is 1 minus epsilon, and the entropy, I just call it entropy, is just 1 minus the capacity for whatever reason. Okay, I mean, we're just defining it like this. So if in general, I did here the entropy, and I think of any binary input channel, Gaussian BSC, and this parameter would be that, and I would plot here, in general, what's called the g-exit function, which is like the exit function, and I would integrate this thing out, okay? Then that's exactly code invariant. It always turns out to be 1 minus the rate, and we'll see trivially why this is true, because we kind of define it that way, okay? Here it might not be completely obvious. And so if we believe this now, then this means that if I now give you many codes, so if I now plot this in general, okay, from let's say 0 to 1, and here I have this, let's say, entropy, and this is like the exit function, then I have always this box here. Then there are different codes, right? So some codes might look like this, right? But maybe that's not very good. Maybe some codes look, you know, I could have a code that looks like this. I could have a code that looks like this. I could have a code that looks maybe like this, okay? So these are all different codes. These would be exit functions of different codes. But the point is that there's no code that's universally better than any other code, right? Because since if I have the code of the same rate, right, since the areas all have to be the same, if anyone is above any other curve for something, they must be below somewhere else, right? Because the area is the same. Okay, so it means there's no such thing as a code that's better than any other code. It's just that for the purpose that we're maybe interested in, they have different, you know, some might be better or not, right? So traditionally, what code, you know, what do you think the code should look like? I mean, traditionally, when we think of a good code, what would be a good code? What should we ask this function to be? Just loud, I can. There's no distance. Maximum rate. So okay, so remember, this is always the rate here. So all these codes, so R is fixed, all these areas under all these things are the same. So let's say take a rate a half code. All these curves have area half. Right? So traditionally, right, I would think that the codes that people, you know, if we're thinking of a good code, so now we're thinking of large length again, right? So a good code, traditionally, people think of this, right? So this means, so this area must be, so this area, this is R, right? So this means this function, so the kind of one extreme case is, right, is that this H star, the critical point where it jumps, is 1 minus the R, right? And so if you think about it different, the rate is 1 minus this H, so this is exactly the capacity, right? So think of so the H, for example, for the BSC would be the binary entropy function of the parameter, right? And you know that the capacity of this channel is 1 minus H2 of the channel parameter, right? So this means if you want the code that in the standard setting achieves capacity, right, then it must have a g-exit function that looks like a step function here, right? Okay, so that must be. And so, okay, so that's kind of maybe trivial, but it also means that if you want that, the code cannot be good above capacity, right? The code has to be as bad as it can be, right? It cannot give you anything meaningful. The extrinsic information that you get, if you want to determine a bit from all the other code constraints, and you tell me that the code is capacity achieving, and I'm not allowed to look at the direct observation, I'm only allowed to look at the other bits and the via code constraints, then if I'm above capacity, it must be that I get 0 information out, okay? Is that clear? Okay, so, sorry? Yes, if this is, let's say, if this is, you know, I have a certain rate and this is my, you know, this is the Shannon limit here, if I'm looking here, right, it must be that this code better give me 0, okay? Okay, so you know, I don't know anything, right? Because, and so the nice thing about it is that we can also turn this around. If I can show to you that for any point above the capacity limit, the code indeed gives me nothing, then I can also conclude that the code actually does achieve capacity, right? Because again, the rate has to be equal to the area has to be equal to the rate. And since if I show you that anywhere up here, this gives me already that, okay, then it must go down. There might be an issue whether or not this goes, you know, since typically it might not be exactly 1, there might be an issue whether or not maybe down there this could be still small but not vanishing. So perhaps you still have to worry about this. But it's kind of clear that what we want traditionally is a shape like that. Make sense? Okay, so now let's just check. So we have something to. So if we want this property, then the easy ways to get it is to build it into the function itself. And so for the BC, again, this is very easy to see how to do it. So, okay, so now, okay, so again, right now I'm writing this down for the BEC, and we'll talk a little bit later on how for general. So I have underlying, I have a code, and now I want this function such that this gives me this area theorem. And so one way to do it is to ask for this. Okay, so let me define the function that we're interested in a completely different way. So let's forget for a second what we're after, okay? And let me just define a function. This will be exactly the function that I drew, to be just the derivative of the conditional entropy of my vector x, right, given the observation y, what I've seen, right? Now, clearly this function, you know, why would this function do, right? Because if I'm going here from 0 to 1, right, and if f of epsilon, the epsilon, right, then what will this give me, right? So I have here just h, so this will be h of x and h of x, y, and epsilon is equal to 1, okay, minus h of x and y and epsilon is equal to 0. Okay, and so I think I should still pick here an n, 1 over n. Right, so I just, again, integrate this out. But what is this, right? So if I have erasure probability 1, then what is my entropy for the x here? Sorry? It's, sorry. Right, so which is what? No. No, this is not in general code. So this is any code, okay? So C is a code, okay? And X is uniform, yeah. So I should have, I guess I didn't specify the model, but okay, sorry. Which is equal to? Oh, yeah, so this is in general any code, okay? So any code, doesn't have to be any linear code, binary code. So the parameter there is n times rate, and then I divide by n. So I get here exactly the rate. And what do I get here? 0, right? So this is just 0. Okay, so this means this here will be exactly a rate, right? So, okay, so far, I mean, that's trivial, right? If I pick that quantity, then I will have the area of him built in, right? There's nothing particularly interesting. So the question is now, what is the connection of this to the thing that I showed you beforehand, right? Okay, so we need some space. Okay, so okay, so I want to start here, and then at the end, I want to come up with something at the end that looks exactly, you know, remember what we had at the end. At the end, I don't know, somewhere, right? We had this probability that xi hat map y tilde I was equal to the question mark, right? We had this quantity here. So I hope to get from here to here. Now, in the previous code, what we had is that there was complete symmetry in there, right? All of the components were the same. Now, in general, these components are not the same. So let me just average out over all of these, okay? And so we'll get something, we're going to get something like this. Okay, so the hope is that at the end we're ending up with this. Okay, now we just need to fill in the steps. Okay, so let's do the following, right? So now let's think of the following here. So I think here that the okay, so what we're thinking is the following. Instead of the total derivative, right? So what does this mean? This just means that I'm turning, I have a knob for the channel quality, and I'm turning a little bit the knob and see how much change there is, right? And now instead of looking at the total derivative, I just write it down as the sum of the partial derivatives. So I'm thinking that each channel is its own channel, has its own knob, right? And I fix everything except for the ith one. I turn a little bit, and then I'm summing these things up, okay? Good, so next step. Sorry. So this is the same, but now I have n parameters, but all these parameters are the same, okay? So this, yeah, epsilon, so all the epsilon, maybe whatever, maybe we should write j, you know, okay? They're all the same. Make sense? Good. So now let's do the following. I want to simplify it. So I'm going to use the chain rule now, right? X, these are all vectors, right? So I have this. I'm going to not write now. This is still the same, but I'm not going to write this down here, okay? Just because I'm too lazy. Okay, all I've done is to write down, to use down the chain rule, right? So I first looked at just xi, right, with everything, and then I have all the rest, and then have the xi on the right. Clear? Okay, any simplification we can do. Sorry? You're talking about this one or this one? Okay. What about this term here? So what is the only dependence? What is the only dependence on epsilon I here? Yi. So maybe more explicitly, right? We could have written here yi, right? Okay, but now what? So these ones don't depend on the epsilon I, right? They have their own parameter, right? So if I turn things, then what happens is that the only thing is what's the chance that the yi will be, what does the yi can do? It can either be equal to xi or it can be erased, right? So, but I have already xi given, right? So what about the yi? Does this give me any information? Right? So the yi contains no information. This is just, just once I give you xi, from xi, just like a Markov chain, then you just go to the x, to the yi, right? That does not depend on anything else, right? So this means this is the same as this, right? But now, nothing here depends on epsilon I. Clear? Okay, so that's this. Okay, so this means we have still this left here, right? Okay, so now I again split it up, right? So when I do the conditioning, right, we have two possible cases, right? So with probability epsilon here, right? This thing here will be, or with probability 1 minus epsilon, this thing here will be equal to what? Xi, right? So we have, with probability, with probability epsilon, so this can be either, right? What we really have is h of xi, we have again xi, right, or y, so yi is equal to xi, and we have y tilde I. And so this is 1 minus epsilon. Right, so this is with, we have one term, or with probability epsilon I, we have this, right? So either the yi is equal to the xi, right? If that's the case, I know that it's the case, right? Because I see either 0 and 1, right? Or with probability epsilon I, it's a question mark, which in case, I also recognize this case, of course, right? And then in this case, I have this. Now, let's look at this case first, right? This is again 0, right? Because I know this, so this, the entropy is 0. And what happens in this case, if it's a question mark, right, then this is like it wasn't there, right? Nothing here depends on the epsilon I, except for this guy here, right? It's just a linear factor. So this means it's the same as 1 over n. Okay, so this is just the entropy of that bit. And now we see why we wanted to have the extrinsic thing here, right? Now this is not exactly yet this, but again, for this simple case, right, either, for the erasure channel, there's no such thing as uncertainty, right? Either I get it exactly, then I know what the bit is, or I know nothing, okay? If I know nothing, the entropy here will be 1, right? And if I know it, the entropy is 0. Clear? So this thing here is the probability that I don't know anything times 1, which is, of course, exactly what we wanted. The probability that x hat map this, okay? And which is exactly what we want. Okay, so this is in principle an entropy, right? But this is the binary erasure channel, right? So for the binary erasure channel, either from the extrinsic bits, I can figure out exactly what bit xi is. Okay, there's only one choice, one compatible choice, okay? In this case, I have entropy 0. Or, if I cannot figure out what this bit is, then I cannot just, it's not like that then I have a 30% chance that it's 0 and a 70% chance 1. Okay, if it's not, then because it's a linear code and because it's a binary erasure channel, the entropy will be 1. It will be equally likely to be a 0 or 1. Okay, and so this will be 1 times the case that I cannot decode. Okay, so it's 1 times, and what's the probability you cannot decode is that this is, sorry, there should be a question mark. Make sense? Good. So, so this thing here, of course, right? So now we see what these things are. So before it was a slightly simpler case, because before we had a case where all these curves were the same, right? In general, these curves could in general be different, and it's the average of these curves that fulfills the area theorem, right? So there could be some bits that I can decode and that have something, and each of the bits can have a different area, but the average of these things is the same. But note that if the code is, for example, symmetric, like what we had, and for example, later on when we talk about Miller codes, this will be even too transitive, then all these curves are actually the same, and then each individual curve has to fulfill the area theorem. Make sense? Good. Yes. For example, we use the fact here that from here to here, because, so then I have an equal number of solutions that have this and that, right? So if it's nonlinear, I guess I could have a different number, and then I would get actually a prior, okay? I'm not sure maybe that's the only step it's used, okay? We'll have to check, okay? But everything assumes the linearity. Good. Okay, so we have the area theorem, and as we said already, even though it's trivial, if we're interested in figuring out a code that is capacity achieving, then it better has a step function. And in particular, one way to show that a code is capacity achieving is actually not to show that it has error probability going to 0 below capacity, but it's actually showing that the error probability is as bad as it possibly can be, the extrinsic above. Okay, if that's fulfilled, I also achieve capacity. Okay, so maybe just, so in the general case, right, so, I mean, just one comment, right, in the general case, this would be still the same. So, I mean, again, so if this is now, for example, the BSC, right, then we know that the capacity for the BSC is, if the parameter is P, is this, right? And so what I call here the entropy, the H is simply this. So, I mean, there's many ways how I can parameterize the channel, but so that we can always draw it in this box from 0 to 1, I always want to keep something like the entropy, okay? That's just a normalization, right? So now I can plot, so, this has the same form, and again, by definition, so this I can again write as the partial derivative, so there will be again these curves. Okay, so will be the Fi of whatever H, okay? So there will be the individual curves, and again, the average of these curves will fulfill it, and so these curves will look the same thing here from 0 to 1. This will be the H. And so I have, again, a similar splitting what I had before, and that these are the individual curves. And what is the interpretation for such a curve? The interpretation is the same. So let's pick one special position, let's say position I, right? So this is x1 up to xn. And so it's exactly the same interpretation. I'm figuring out the extrinsic estimate of this bit here. So what I have is the axis. This goes all through the channel. I see the y. And so I want to estimate, again, the x hat for the I. Okay, so I can write down the estimator here. But maybe it's nicer, instead of writing away the estimator, let's just compute the log likelihood. Okay, so I'm computing the log likelihood. So in general, for general channels, it will not be true that I can either figure this out or not. It might be that I get simply a certain log likelihood ratio, maybe 0.3 or something that tells me it's so likely to be a 0 and so likely to be a -1. But what's important is that, again, when I do this estimate, it's only based on the extrinsic bits. Okay, so I'm not looking at the observation directly. I'm not looking at the yi. Okay, I'm hiding the yi here. I'm only allowing to look at the rest, and then I have an estimator based on the rest. Is that clear? Right, so I'm just looking at the code constraints and the other and all the other observation, and then from that I'm trying to come up with my estimate of bit I. And of course, if you now wanted to then have the best global estimate, you would combine that with the direct observation, right? So you have the estimate that comes from the other bits, you have the direct observation. If these are likelihoods, and since these are two independent estimates, what's the optimum estimator if I give you two likelihoods? I give you two, I have two conditional independent observation, one direct, and the other one via the code bits, right? And I compute L1 and I compute L2, and the best combination is then just the sum of the two, right? So, sorry? Log likelihood, sorry, okay? So so this is the same, exactly the same story. So the interpretation of this Fi, okay, will simply be, so what do you get in general? You run the following experiment, you choose a code word, you send it over the channel does whatever it does, you compute here the log likelihood ratio, okay? And so you do this many, many times, and so if you do this many, many times, what you will get is you will get some kind of distribution, right, for this log likelihood. Clear? And so this distribution here, right, acts like a channel. This is like the observation itself, right? You have also, there's the channel itself, but you have also log likelihood distribution of the intrinsic information. And that you can think of like a channel, and this channel has an entropy, right? And it's exactly this entropy that you plot here, okay? Or you take the derivative of this entropy when you're changing the h, and that's exactly what the exit function is, okay? If, you know, it's not super important right now for the general case. I'm just going to talk about the BEC, but all the things I said, area theorem, and all these things you can do in general, okay? It's just no longer, it doesn't give you this really nice formulation that's exactly equal to the probability of erasure, okay? It's a quantity that's a little bit not as nice to interpret. Clear? Okay, so now, so I told you already what you want. So now let's get to a, oh, we're already way past time. No, when? We started at 38. Okay. So now, so this area theorem will be important in both instances, but now let me right away start for how we use the area theorem for the spatially coupled one. So I want to give you basically a first application, you know, why the area theorem is, you know, is useful. And right now we are not even talking about spatially coupled codes. This will come a little bit later. But right now I just want to give you a very simple bound on the map performance of LDBC codes based on the area theorem, okay? So remember what we had. For low-density Perry-Check codes, we had something like this. And I'm always going to use the same example, something like a 3.6 code. Again, this could be anything, but just to keep things simple. Right, this thing here is n. You should think of n going to infinity. And then you have 1 minus r times n check nodes here. So now, generically, we know, or I told you, how we can figure out how this performs under iterative decoding. Okay, so let's just maybe recall. So just to keep things simple again, we again just assuming the binary ratio channel, and we are interested in under performance under iterative decoding. Right, and so what happens is I pick a code word due to symmetry, it doesn't matter which one, could be the all 0. Some of these things will get erased. And some other ones I'll see the actual bits. And now I run a certain number of iterations, and I would like to know what's the fraction of bits that I can actually recover, right? And so remember what we did. We sent the erasures over there. We did the computation. We went back. And so if you think now of the code large and you think of a fixed number of iteration, what's really happening is that you're having a support tree. So if you're looking at what happens, for example, to this bit here, right, then this bit here is connected to a certain number of checks. Okay, and so what I'm going to do is I'm going to draw this outside here. So this bit will be connected to 3 checks, right? And these checks internally are connected to some, and there will be 5 other ones of these bits. right? So all I'm doing is I'm unraveling the support tree, the computation tree that you have here, right? So what happens is that I'm interested in the value of this bit, and let's assume I'm not allowed right now to look at the bit itself. I want to know via the code constraint, the local code constraint, what this bit is, right? So each of those bits is erased with probability epsilon, right? And if I'm thinking of a fixed size number of iterations, okay, and we can later talk about the order of the limits, but right now to keep it simple, if I'm thinking of a fixed size of iterations, and I'm thinking of this tree becoming large, right, then the probability that all these bits here are different bits, that there are no repetitions in these computation trees, goes to 1. Is that clear? Okay, so it won't be that this bit is this bit with any positive probability. Yeah, so you have to worry then, for the erasure chain, it's very easy to see that the order doesn't matter, okay, so you could do an infinite number of iterations, or you can basically first take a fixed number of iterations, let the limit go to infinity, and then take the iteration number to infinity, or the other way around, you will see that you get the same result. But the analysis is more complicated, so that's why I want to just look at the simple case, or the simple analysis, where the number of iterations is fixed, n goes to infinity, we analyze it, and then we're thinking of the number of iterations going to infinity. Make sense? So what is the probability that this thing here is erased? Right? So here, the probability is epsilon, right? So the check note, what is the probability that this thing here is the erasure probability? When is it the erasure? It's not erased if all of them are known, right? So let's assume it's the 3, 6. So it means this probability is 1 minus, and it's the same that we already have seen, right? It will be something like this, or if I write this down in general, it's r minus 1. Right? That's the probability that this thing here is erased. Make sense? And now what is the probability that this thing here is erased? I'm not allowed to look at the observation itself. Well, if any of them is, it's only going to be erased if all of them are erased, right? So this means this is erased with 1 minus epsilon to the r minus 1 to the L. Right, so my simplest one iteration extrinsic estimate, right, just one iteration, I'm just estimating this thing, will be this, right? Now, of course, I could do better. So this would just be what I get after one iteration. Of course, I can do better, and we'll talk about it in a second, if I did several iterations. But let's just see what we get from this trivial estimate here, right? Okay, so now remember. Okay, so this will be my estimate after one iteration. And if I did several iterations, I would get a recursion like that. Okay, so the recursion would look something like this. X0 is epsilon, x, y, whatever. L is 1 minus xl to the r minus 1. And x, L plus 1 is something like epsilon 1 minus yl, sorry, 1 minus yl to the L minus 1. And then the estimate would be something like, let me call it x hat, would be y to the, oh, the L is not good. Okay, it's very unfortunate that I look the index to be equal to this. So let me call this maybe capital L here. Okay, so if you didn't this estimate just after one iteration, but you did it after several iterations, then initially you send out epsilon from the erasure thing. This is this is the probability, the erasure probability coming back. And if you then go further, if you just do the, not the estimate itself, but you go further, you see the bit itself and you see the other ones. You have L minus 1 extrinsic ones, you go up. And at the end, if you do the extrinsic estimate, you just take the input and take it to the Lth power. Okay, so if you visualize this just for L is 1, then you get exactly this estimate here. Is that clear? This is the iteration. That's called density evolution. Okay, so now, you know, in general, this is a suboptimum estimator. And in general, this will either converge or it doesn't converge. I mean, it will always converge to some fixed point, but might not converge to actually do full decoding, right? So what I claim is that this, together with the area theorem, we get actually a very nice bound on the map performance of this code, right? This is a suboptimum decoder. You know, it has absolutely nothing to do with the optimum performance of the code, right? Okay, but the claim is the following. So whatever this exit curve is of the code, okay, I don't know what the exit curve of this of the code actually looks like. Maybe it looks like something like this. Sorry. Yeah, this is the iteration number. Right, and right now I'm just looking at the estimate after the first iteration, but I'm saying you can get better estimation after other ones, and we'll come back to it later on, okay, to look what the optimum is. Okay, so if you did that, so remember, so there would be the actual exit function of the code. The actual exit function of the code would be the map performance, right? Now, in general, it's actually very difficult to figure out what the map performance of the code is. Okay? And actually, the only method we know what the map performance is will be exactly the way I'll tell you to do it. Okay? If I give you now, let's say, a 3/6 code, and I tell you if you could do the code this for, you know, length goes to infinity, you take a Gaussian channel, and tell me up to which threshold this code could decode correctly, right? Then I could, via dense evolution, compute how under the suboptimum decoder it would do. The equations would look more complicated for the Gaussian, but would be something like this. But if I ask you how to do it for the map, it's a very difficult problem, okay? So now, any idea how we could get an upper bound on the threshold by using the area theorem and what we have? Sorry? Just louder, please. Right. You can prove poorly. So remember, if this is the exit curve, the actual map performance, then we don't know, right, what this curve looks like. But we know that this is equal to the rate of the code in here, right? Now, is there any way that I can bound this curve? If I could find an upper bound on this curve, what could I do? Sorry, or if I could find, let's say an upper bound. So let's assume I had a curve. It's hard to draw now. Let's assume I had a curve that would look something like this, okay? Whatever. Doesn't matter, okay? All I know is that this curve is above this curve here. What could I do? All I guarantee you is have a curve that's above this curve. Okay, this curve I don't know. And so I don't know what the threshold is, right? It might not even have a threshold. It might even go down like this, but okay, let's assume it has one. But on the actual exit curve. Okay, this is some curve you magically tell me this is an upper bound. So what I could do is the following, right? I could look at the point where this, the upper bound, has equal to the rate of the code, right? Clear? And what would I know about this point here? Right? So this point would be an upper bound on the actual thing here, right? So if a priori, all I want right now is an upper bound on the map threshold. So for example, I want to show you that this code for sure doesn't achieve capacity, so it's away, right? So I could do that. Now, what would be a natural upper bound in our case? The all one. You know, then you just prove you cannot surpass capacity. claim it's on the board. We're looking for something that's worse than the map. So what is the special thing about map decoding? Right? So the map decoder, by definition, right, has the lowest probability of error, anything, right? So if I give you any other decoder and I analyze the performance there, it must be worse, right? So in particular, I can give you this curve here, right? So I can plot this curve here. So if I plot the curve, if this curve here is the curve epsilon 1 minus epsilon to the r minus 1 to the L, right? I can plot this thing here. And if I do this, let's say, for the 3.6 code, right? And I just do one iteration, then I get, just try to see, I get already an estimate. Okay, I can't find it. Okay, I don't have it, but I think it's 3 point whatever. It's so if you do this for the 3.6, you get that this epsilon map upper bound, okay, is equal to 0. I think it's 496 or something. Okay, I can't remember, 0.49 something, but it's less than a half, right? Now, so this means it's already a non-trivial upper bound, and so if you go further down and do this for several iterations, okay, so you do 1, 2, 3 iterations, you will see that this upper bound goes down to 0.48815. Okay, and it turns out, and we'll try to get there, that this is exactly the map threshold. Okay, so it turns out that this bound, this trivial bound, by just plugging in the better and better estimates that you get from the iterative decoder, that this converges exactly to the map threshold. Okay, so this is not completely trivial because we have used here the BP not as an algorithm. Okay, we have used here a kind of an algorithm that has nothing to do with optimum decoding to come up with an actual bound for the map. Okay, and once we're done with spatially coupled, hopefully we'll see that this is indeed exactly, via the spatially coupling, this will also not just be an algorithm, but also a proof method. We'll see why that actually makes sense that we get exactly the upper bound or the exact bound for the map, not bound, the exact performance for the map threshold.
Various curves will be different decoding algorithms and what they are able to achieve because you had map.
Yeah, so this is the map here. Now we'll have different curves. These curves will be monotone, go down, so you get better and better bounds, okay? And so we'll get some limiting bound, which is something like this. And it turns out that that's equal to the map threshold, okay? And so the spatially coupled won't just give us that we have good codes, but it will also allow us to actually tell us what is the map threshold for these codes. Okay, and so I think I'll quit at this point, and I hope that tomorrow I'll get this story still across. We'll see how it goes. Okay, and then afterwards we'll talk about Reed-Miller codes and thresholds and Boolean functions. Okay, thanks.